Great. Good afternoon, everyone. My name is Michael. This is Dania. That's Patricia, and we're the methane hydrate combustion team. I'm going to leave it to Patricia to explain the background of our senior design project.
So, I don't know if any of you guys know what exactly methane hydrate is, so we're going to go over like that. So methane hydrates are molecules of methane trapped inside a layer of ice, and these are formed under high pressure and low temperatures, which are ideal at the bottom of the ocean. Currently there's a lot of universities and laboratories trying to extract this methane hydrate from the bottom of the ocean because it's a big energy source. The University of Texas actually estimated it's about 250 years worth of natural gas that is currently trapped there. So that is why everyone's trying to extract it. However, while people are trying to extract it, methane is extremely flammable. And there's no defined characteristics of methane hydrate combustion, so that is what the Keck laboratory here at ACI is trying to focus on. And we, as a methane hydrate combustion team, we're trying to design a chamber that allows for this testing of methane hydrate combustion. So our goal is to design, construct, and test a combustion test chamber that can accurately record emissions of a 50 cc methane hydrate sample using an NRX 700 probe. So our customers are the Deep Ocean Laboratory and the VEEB, which is a PhD student currently studying methane hydrates. And we actually have a design that was made from a previous team last year, but it was not, although it was completed, it is not functionable. So what we're trying to do, we're using this chamber as a resource as we're constructing a new one. So our 4 main objectives for this project is to design a chamber that has laminar and uniform airflow, which will enable full combustion of the methane hydrate. And this device should also have a weight measurement device that allows for the recording of the 50 grams or less of methane hydrate while it's in combustion. Another thing is we need to select an appropriate RH meter to measure water vapor emissions while the methane hydrate is combusting, since it is enclosed in water. And then we also need to verify that this chamber enables for accurate emission readings using the NRX 700 probe, which is this display here.
Alright, so utilizing the previous objectives that were listed in the previous slide, we were able to create a specification sheet or a needs metric matrix sheet that lists our specifications shown here. And based on these specifications, we were able to calculate experimental calculations and theoretical calculations. And from there, we were able to create a marginal and an optimal set of values for each of the following specifications in order to create an optimal design chamber for methane combustion. So just to list out a couple of them, the first one, as we previously stated, we use an NRX 700 probe, which measures the the emissions of the combustion of methane hydrate. And so we've done previous tests in lab. We've obtained numerical values for these. We've also utilized the theoretical calculations from stoichiometric equations involving a lot of chemistry. And from there, we were able to, we would like to have an optimal percent error of 2.5% by comparing experimental and theoretical. Another one that I would like to point out, which is very important, is excess air. So we were able to obtain this criteria by doing, again, test results and theoretical calculations to provide us with a range of how much percent excess air we should have. So next. So this is just our subsystem breakdown. In order to create a combustion test chamber, we first want to look at the case structure. Within this case structure, we would like to have a combustion chamber that has suitable flow, which is laminar and uniform. And then also we would like to have emissions, we would like to analyze our emissions in order to provide accurate emissions data. And also we would like to actually see the combustion of the methane hydrate, so visibly see the flame. So another component of it is data acquisition, finding the necessary instruments that are needed. To calculate, to measure emissions, we need the NRX 700 probe, as mentioned before. To measure the flow rate, we need a rotometer. And then to measure the weight, we need this program that's called DOP4 in order to measure the liquid water and the methane hydrate weight. And then we also need an RH meter. Next, in order to, the last component that we need to create an optimal test chamber is the air inlet, in which we need suitable flow, which again is laminar and uniform, and we also need to measure excess air. So the resources that we have available to us is the Keck Foundation Deep Ocean Lab. So that provides us with the necessary equipment, all of the strain gauges, the probe, everything, the desktop computer. And so myself and Michael and Patricia, shown here, we've accumulated a total of 112 hours that we worked on this project. And we've met twice a week since week 2. So it's been around 12 meeting hours, and then we've also had 5 lab hours where we actually perform testing. This is the structure of our, how our team is. So we have our leader, Michael, and we are the 2 general members. This is a previous member where we obtained, he graduated, we obtained the SolidWorks files from him for the previous design chamber. And also our customer is Naveed, and our academic advisor is Derek Dunrankin.
So this is our timeline for the project. We aim to, by the end of this week, to actually have our specifications and parameters actually made and determined. But by week 10, we actually want the drawings, the material selection, SolidWorks files with actual dimensions actually finished and completed. But and then for the second quarter, near the end of week 7, we want to actually have the prototype actually constructed and fabricated. But in the meantime, from week 4 all the way to the third quarter, spring quarter, by week 8, we want to actually make methane hydrate samples. We want to burn them in various test cases like open air combustion, maybe with last year's combustion design, as well as our own prototype design. And then by the end of the whole academic year, we would have to present this test chamber to the laboratory. So we did a lot of things, but these are the main highlights of the progress that we did, step by step. We decided to use gel ethanol instead of methane hydrate to begin with, because methane hydrate actually takes a full day just to make. So it's too much of a time constraint for us to really commit to that just now. So we use gel ethanol since it's a solid hydrocarbon fuel, just like methane hydrate. So we performed experiments with combustion with that. We used an NRAC probe to measure emissions, as well as measured the weight that is lost over time during the combustion process. And using that data, as well as our customers' data for methane hydrate combustion, because he actually did do some experiments in the past with open air combustion for methane hydrate, we used those data points and determined the actual mass loss rate and combustion emission concentrations. And from those values, we actually determined the volumetric airflow rate needed to combust it, as well as the required excess air concentrations for more complete combustion. From those values, from the volumetric airflow rate, we actually decided to put that into the SolidWorks files. These are the dimensions for that current test chamber, that's last year's. But we also did 2 alternative designs for the air inlet system. We have one that's a single hole air inlet, as well as the multiple ring. I don't know if you can see right here where air is being pumped in, around the bottom of the test chamber. So far, preliminary analysis, this is obviously not very laminar. It's kind of crazy vortices and all that stuff. But the speeds are actually a bit better. I think they're around 25, 50 meters per second. This one, however, with the volumetric flow rate that we determined from our experiments, it's actually supersonic, so it's not going to work. So we have to actually reevaluate our methodology to see if maybe there's something wrong there, or maybe we have to do something with our design for the air inlet system to provide the air needed to have more complete combustion. In the meantime, I also was doing some research for vendors that could provide like relative humidity meters for water vapor emissions during combustion. And I found a measuring device from Vaisala, so we're doing good there. This is our current budget. It reflects all the needs of the things that are needed right now that aren't currently supplied to us. So that would involve obviously the relative humidity meter. That also involve like rotometers as well as strain gauge for load cell. But this is actually subject to some change because the laboratory could actually provide some of these instruments. Like the rotometers, they have a huge box of rotometers of various ranges to use. It's just that we can't look through all of them by this point. As well as the strain gauges, they might have some extra lying around that we could apply to the load cell in order to test for weight measurements. And that finishes. Is there any questions?